Hello everyone, we are Group 9, and this is the EOG electrooculogram based alert system for aphonic amyotrophic lateral sclerosis patients.
Hello, my name is Joe Ham. My concentration is in biomechanics, and my role was the design inputs and verification design.
Hello, I'm Josh Hanneman. My concentration was in biomechanics, and my role was engineering and algorithm development.
My name is Arthur Spiros. My concentration is in neuroengineering, and I worked on verification and validation design.
Hello, I am Molly Walsh, and my concentration is in biomechanics. My role for this project was engineering and medical correspondence.
My name is Tyler Yang, and I'm a bioinformatics concentration, and my role in this project was engineering and algorithm development. Our team advisor was Dr. Doherty.
Presentation, we will introduce our project by defining the need, setting the design inputs, reviewing the solution paths, proposing our intended path, and how we plan to execute it all. Before we get into the presentation, it is important to define any abbreviations or terms we may use throughout this PowerPoint. ALS is amyotrophic lateral sclerosis, EOG is electrooculography, EMG is electromyography, LIS is locked-in syndrome, and the term aphonic is defined as the inability or the loss of speech. So, what is ALS? ALS is a progressive neurodegenerative disease that affects nerve cells in the brain and spinal cord. ALS usually strikes people between the ages of 40 and 70, and approximately 20,000 people in the United States have the disease at any given time. Caring for a person with ALS is an everyday task that can become extremely costly. The current estimated out-of-pocket cost for caring for a person with ALS is $250,000 a year. To this day, there is no cure, and after diagnosis, the average life expectancy is 2 to 5 years. So, how does ALS progress? The symptoms of ALS and the rate of their progression vary from person to person. However, there are symptoms associated with different stages of the disease. In the early stages of ALS progression, patients tend to have weak muscles. It's common for them to experience twitching and muscle cramping, as well as loss of muscle bulk. The symptoms may occur in only a single region of their body, or mild symptoms could affect more than one part of the body. This stage often occurs before a diagnosis is made. In the middle stage of ALS, the symptoms in the muscles become more widespread. Some muscles might become paralyzed, while others are unaffected or simply weakened. Weakness in the breathing muscles can result in respiratory insufficiency, especially while the patient is lying down. Some people begin to experience uncontrollable and random bouts of crying and laughter. This could be due to a cognitive decline. By the final stage of ALS, most voluntary muscles have become paralyzed. The muscles that aid in the moving of air in and out of a person's lungs are severely compromised. Mobility by this point is severely limited, and the person will need help in most of their daily functions. Respiratory insufficiency is the primary cause of death for those with ALS. Now we will have a closer look at locked-in syndrome. So, what is it? Locked-in syndrome is a rare neurological condition in which a patient is fully conscious yet completely paralyzed and aphonic. Currently, there are 3 classifications of locked-in syndrome: classical, incomplete, and total. While all show some lack of voluntary muscle movement, the main difference relies in the retention of vertical eye movement. Currently, there is no cure for locked-in syndrome and no standard of treatment. A major problem that lies in locked-in syndrome is that the patient loses their ability to call for help. As an ALS diagnosis progresses, respiratory failure becomes an urgent need, and without an ability to call for assistance, death becomes a possibility.
As stated previously, those in the later stages of ALS are extremely limited in physical capabilities. Most have lost the ability to speak, and in more severe cases, only the ability of vertical eye movement is retained. As a result, most patients rely heavily on caregivers to ensure their safety periodically. While simple and reliable, this form of help leaves a great deal of time in between check-ins where the patient is left unable to call for help. To aid in this process, many call bell devices have been created to grant users the ability to signal for help when a carer is not there. Unfortunately, most devices currently available on the market are either too complex or require some skeletal muscle control for activation. Our team aims to grant help to those excluded from the current pool of urgent care call bell devices.
The existing solutions for ALS alert devices can be broken up into two categories: call bells and a call bell communication hybrid. Call bells typically feature a combination of a switch and an alarm. While these are great tools for ALS patients in the early stages of the disease, they are more limited as the disease progresses. This is due to the fact that call bells require some voluntary muscle control to operate. The hybrid devices typically feature an eye tracking software. While they do not require voluntary muscle movement, they do require a large cognitive load. Patients in the later stage of their ALS progression have been found to have a cognitive decline. Therefore, this device does not work out as well. It is also important to note that none of the devices listed above were especially designed for ALS. We plan to develop an EOG-based communication device that is oriented for use on aphonic ALS patients in an at-home care setting. This will allow patients to ask for help when an urgent need arises and will ultimately enhance the communication between caretaker and patient.
The universal constraints of this project include a May 2021 deadline, a $1,000 budget, and the resources provided by Drexel University. Here are the design-specific constraints. Since this is an extension of a prior project, we are constrained to the use of the prior EOG mechanism. The device should be fixed to the body to compensate for difficulties in maintaining posture. Training and use of the device should be accessible with respect to the patient's cognitive decline. The device must be affordable to home care and must abide by FDA regulations for Class 1 and Class 2 medical devices. Here are the requirements. Our device must have a sensitivity greater than or equal to 97% to urgent distress calls. This is important so that the patient is able to accurately call for help and have their needs met by the caretaker. The battery life must exceed 8 hours and the device must function in between a range of 0 to 20,000 lux. The wide range of lux testing is to encompass each home, which has unique light settings that the device must function in. Furthermore, the device will be used throughout the night in which a very low lux is possible. The range was determined based off of recommended standards. The alert must sound at greater than 55 decibels, and the alarm signals must be received throughout at least a 30-foot range. The range of the alarm must exceed this in order to avoid limiting the caretaker and also avoid failed signal generation. It is important that the patient is able to generate a signal within 20 seconds of distress, since a patient may lose consciousness under cardiac arrest in 20 seconds.
Our verification process will include various testing procedures assessing the efficacy of some specific device components and overall sensitivity. Device sensitivity will be tested both before and after 8 hours of use, each time prompting patients to output distress signals at random time intervals. The sensitivity test will also be conducted at varying distances away from the patient to test the strength of the device's signal. Finally, our device's capability of outputting a sound at our proposed level of 55 decibels will be tested using the smartphone app Decibel X in conjunction with a calibrated external microphone.
This traceability matrix denotes the need that is being met, verified, and any potential issues during the process. Patients are in need of attention greater than or equal to the attention received in hospitals. A sensitivity greater than 97% will be verified to meet this need. A potential issue is that we are limited to test subjects for these verification protocols. Patients are in need of constant monitoring throughout the night, which will be fulfilled by a battery life of the device greater than 8 hours and flexible lux functioning. Respectively, an appropriate battery and controlled light booth or room still need to be determined. Patients are in need of an autonomous mode of call for help, which will be fulfilled by proper alert decibel levels and signal range. Potential issues include varying architecture in the home, which may pose obstructions contributing to damping of sound and/or signal. Lastly, patients are in need of a quick mode of help. The device will allow for signal generation within 20 seconds. It will be difficult to replicate the characteristics of ALS patients. Therefore, a diverse group of test subjects will be sought after to mitigate this issue.
Here, I will outline the core functionality of the EOG signal module. Firstly, a patient will generate eye movement, which will be picked up by EOG electrodes. The previous project used EOG electrodes provided by Bitolino. This signal is then processed by the signal processor with varying calibration specifications. Our predecessors used Raspberry Pi with Python and calibrated according to a universal threshold based on one patient's frequency of voluntary vertical eye movement oscillations. When the threshold is reached, the signal will be relayed and then output to the caretaker, alerting the caretaker of distress. The previous project's mechanism used a Bluetooth signal relay and an audio signal output. This is a diagram of our proposed additions. We've included an auxiliary signal to the initial EOG pathway. When coupled with the EOG signal, it is possible to provide a greater range of communication to the signal processor, as well as enhance signal fidelity. A feedback signal is also proposed to address the limitation that the prior project had a high rate of false negative outputs, likely caused by the universal threshold, providing no response as to whether the signal had been output or not. Because the EOG signal will be a spectra of different oscillation frequencies, this feedback signal will provide a scaling response such that the patient feels control over the device, improving rates of successful voluntary outputs and enhancing patient autonomy. In this matrix, the 7 columns correspond to the 7 Roman numerals in the signal diagram, signifying slots to fill our final solution path. In green are options that suit the core functionality of the EOG and are relatively readily available. In orange are options that would provide extended functionality and performance to the EOG, but not necessarily to the function of the core EOG, in the case that time limits the scope of this project. Firstly, EOG orientation was chosen to be vertical to suit the available range of motion of most ALS patients as possible. The horizontal, diagonal, and hybrid features would cause a significant population of late-stage ALS patients to lose full functionality of the EOG device. The signal processor will continue to use Python, as the previous code was developed on it. There would be an advantage in structuring in Java, and the code would be lighter weight in C, but for the scope of this project, the transition would probably be more trouble than it's worth. The calibration method being oriented around a universal threshold would be easily accomplished, but a self-instructed method of signal processing and threshold generation could be developed with time. The most basic signal relay mechanism would be hardwiring, while an SSH protocol could connect all devices wirelessly using a Wi-Fi source as a relay, significantly increasing the range of operations of this device. The signal output will remain in audio format, as this grants the most versatility and range for the receiving end of the device, when compared to visual outputs requiring a second monitor, and the haptic feedback option requiring direct contact with the caretaker. The auxiliary signal will be an EMG monitoring eyelid to encompass the greatest population of ALS patients while accounting for visual errors such as droopy eyelids associated with late-stage ALS. Finally, the feedback signal will be vibrational to enhance the patient's feelings of control and autonomy, as well as the vibrational motor being the most economical options among visual and audio outputs.
Here we have the total project schedule exhibiting all the necessary phases of our project. On the following slides, I will be going into further detail of this timeline. Here's the first phase of our project, which includes defining the need and goal, the constraints and requirements, the solution path that we can design, our design plan, followed by our verification plan. Currently, we have finalized our need and goal for the project, along with the constraints and requirements. We've created the necessary solution path to fit the need and goal of our project, and are currently deciding among the group which path we want to take. After that, we will finalize our design and verification plans based on our current list of requirements, constraints, and solution plan. Here is the design and testing phase of the project, which is intended to start at the beginning of the winter term. However, we plan to begin as soon as possible. On the following slides, I will detail the necessary steps of the project and roles of each of the team members. Here is the first design phase of the project. This phase includes the examination and build of the prior team's device that was developed the previous year. Arthur and I will be working together on the circuit design and development. At the same time, the algorithm connecting to the Raspberry Pi can be examined and developed based on the previous year, since we will be using the same coding language. Tyler will be taking charge of this aspect. Shortly following, Molly and Joe will help by determining the correct placement of the electrodes around the face, so when the time comes, we can start testing the EOG. After the device is complete, following our updates, we will test the signal of the EOG chips and relay to the Raspberry Pi. Arthur, Tyler, and I will be working together to complete the last steps of this design. This is the second design phase of the project. This phase can start at the same time as the first, as long as we are able to, with the development of the dynamic feedback algorithm and the device, which will be taken care of by Tyler for the code and Molly and Joe for the design and development of the dynamic feedback device. Following the build of the device, Arthur and I will begin the circuit design for the feedback mechanism. Then the team will begin the calibration of the mechanism and device to determine the correct vibrational setting. Here is the third and final design phase, including the testing and final preparation stage of our project. While not absolutely necessary to complete the goal of our project, we've included time to develop an auxiliary signal into our project design. Time permitting, we will begin by creating the algorithm to determine the auxiliary signal taken charge by Tyler. And shortly following, Arthur and I will begin circuitry to include EMG chips and extra electrodes. Molly and Joe will begin on determining the correct placement of the EMG to determine the best signal that we can get so that we can begin testing the device as soon as possible. The whole team will work together to test the device against our verification protocols that we will develop, finalizing the project with the team working on the final presentation and documentation of our project.
To give everyone a small update on the status of our prototype, I've included images of our inherited schematic of the core EOG module, as well as an image of the physical model. As you can see, the breadboard encompasses analog to digital converters and inbound EOG electrodes. The Raspberry Pi model is a lighter weight and slightly older model compared to another available device, making it possible to upgrade processing power and storage at a later point in this project. At the present moment, this device is non-functional, and our engineering team is working with the algorithm team to assess the cause of it. Because the circuitry does not directly correspond with the schematic, it is possible that this device is in an inappropriate configuration, or possibly that the code is reading from the wrong terminals, returning errors. When spare parts become available, we will be more comfortable in deconstructing this device to troubleshoot. At the same time, we are researching and working on procuring the necessary parts for our proposed additions. For the feedback, we are looking for a cheap DC vibrational motor and working on creating a 3D printed housing unit such that the device may be strapped onto the arm. For the auxiliary input, we are looking into sources for EMG parts compatible with our breadboarding configuration. Ideally, this mechanism would be minimally intrusive and generate signal in tandem with the EOG unit. Thanks for watching this presentation. That's all for now. We'll be happy to take any questions. A myotrophic lateral sclerosis.
Sclerosis.
A myotrophic lateral sclerosis.
Sclerosis, yeah.
Sclerosis?
Sclerosis.
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 Yeah.
Sclerosis.
And then barf.
Rhoda.